e.g. 11005, Projects. IT Skills, Topic 2, Spreadsheets. This is the first part of our lecture about Microsoft Excel. We will look at the subjects required to produce correct calculations. In this part, we will look at how to work with Excel, cell referencing, graphs, functions, and processing data. In part 2, we will have a look at some more functions and formatting. Excel's potential. Excel can perform many and varied calculations using an enormous range of functions. Functions are divided into several groups that include finances, date and time, maths and trig, statistics, lookup and references, databases, text, logic, and information. Excel can also be used for storing data, drawing graphs, and displaying data in diagrams. Typical engineering uses. Typically, engineers use Excel for processing data from experiments, generating data for parametric studies, and simulating calculations. Essential elements. When using Excel, it is essential to plan what you want to do. Use named cells and ranges where practical. Build complex equations in stages before combining. Formulas should be built using BODMAS rules, which stands for B brackets, O order, D division, M multiplication, A addition, and S subtraction. Make clear formulas. The BODMAS rule means that mathematical expressions with multiple operators need to be solved from left to right in this order. Remember that division and multiplication are considered interchangeable and depend on which comes first in the expression, as are addition and subtraction. Here you can see an example of a formula initially typed with unnecessary brackets. When BODMAS is applied, it removes all unnecessary brackets. The use of BODMAS can be essential in building complex functions such as this one. Cell referencing. Let's now discuss what cell references are and how we can use them in formulas. There are two methods for cell referencing in Excel, which include the standard method and R1C1 style. Both methods are based on referencing cells by their columns and rows. The difference lies in how the columns and rows are named. The standard method is based on naming columns using letters and rows using numbers. For example, a single cell referenced as H4 means that it is in column H and row 4. A block of cells is referenced using the top left and bottom right cells. For example, block G3J20 is defined by the cell in column G and row 3 and the cell in column J, row 20. In the R1C1 style, both the row and the column are named using numbers. The difference between the two is in the letters. R and C used to signify rows and columns. For example, R3C7 is the reference to a cell, row 3 and column 7. The R1C1 style can also be used to denote relative position using square brackets. For example, R, -1 in square brackets, C, 8 in square brackets, references a cell located 1 row up and 8 columns across from the selected cell. The same rule is applied for referencing a block of cells. For example, the reference R3C7, R20C10 describes a block of cells defined by the cell in row 3 and column 7 and the cell in row 20, column 10. As you can see here, relative positions of cells can also be used in defining blocks of cells. Unless it is stated otherwise, we are going to use the standard method for cell referencing in this lecture. Simple formulas. Let's discuss how to use cell referencing in formulas using the multiplication table as an example. Excel understands that you type a function in a cell when you start with the equal sign, as shown here. To build the multiplication table, we created in column A and row 1 a sequence of numbers to be multiplied. Then, in cell B2, we multiply the cells B2 and C1. Note that these cells are located immediately on the left and top relative to cell B2. For clarity, Excel coloured the references and the borders of the corresponding cells in blue and green. By pulling the handle of cell B2 right to cell C2, we copied the formula from cell B2 to C2. The process of copying saved the relative positions of the cells referenced in the formula of cell B2, which led to the product of cells B2 and C1 in cell C2. However, we require cells A1 and C2 to be multiplied in this position. By pulling the handle of cell C2 right to cell D2, we copied the formula from cell C2 to D2. The value in cell D2 equals 6, but it should be 3, which is a product of 1 and 3 in cells A2 and D2. The formula in cell D2 is cell C2 times the cell D1, and that means that the relative positions of the references were preserved again. Absolute cell referencing. We found that formulas in copied cells down the way increase the row number, while formulas in cells copied across the way increase the column number. Often it is necessary to keep a reference to constant cells. The reference to column or row can be frozen by using the $ in front of the column letter or row number. This can be done by introducing the $ by hand, when necessary, or by pressing the F4 key. The latter action will start a cycle going through 4 options, including freezing both the row and column references, freezing the row reference only, freezing the column reference only, or unfreezing any references. Now we need to amend the functions in the cells by freezing relevant references. Let us start with cell D2. First, we change the reference to cell C2 to cell A2. Now we need to freeze the reference to column A. To achieve this, we press the F4 key 3 times. Now we need to freeze row 1 in the reference to cell D1. This is achieved by pressing the F4 key twice. As you can see, this resulted in the change of the cell value from 6 to 3, which is correct. If we use copy now, the expression in cell D2, it should keep the references to column A and row 1. First, we drag the border handle left, and then we drag it right. These actions result in a first row of the multiplication table. And next we can drag the handle down, which populates the entire multiplication table. Named cells and ranges. Individual cells in a spreadsheet can be given unique names, which can reflect the meaning of the values in these cells. These names can be used in referencing the cells instead of using cell positions in the spreadsheet. In addition, this practice makes formulas much easier to understand. Consider, for example, the following formula typed using cell position references and cell names. The second version of this formula is much clearer. Naming cells. Cells can be assigned names in several ways. First, it can be done by typing a name in the name box. Alternatively, names can be assigned by going to the Formulas ribbon and clicking on the Define Name icon. Other methods are to use the icon Create from Selection from the Formulas ribbon and to go to the Name Manager. Name box. First, let's discuss how to name cells using the name box. The name box is located above the top left corner of the spreadsheet. Currently, it shows B2, which is the reference to the selected cell. To assign cell B2 a name, we click on the name box. As you can see, the reference to the cell is highlighted. Now we type in the box a name selected for this cell. In the example considered here, we name cell B2 as Span. To approve the name, we must press Enter, otherwise the cell stays unnamed. Define name. Another method for cell naming is to use the Define Name icon in the Formulas ribbon. Clicking this icon brings up the New Name pane, which allows setting a name to a cell referenced in the Refers to box of the pane. In the example considered here, we name cell B3 as Rise. After clicking OK, the name of the cell changes to Rise, which can be seen in the name box. Create from selection. Multiple cells can be made using the option Create from Selection in the Function ribbon. This option allows us to name cells in a column using text in the cells of column A. To do this, we select the cells with the text in column A and numbers in column B and click on the Create from Section icon. The pane Create Names from Section appears. In this pane, we select the column or row with values to be used for naming cells. As you can see, the left column is selected in this example. Click OK to approve the naming of the cells, and this results in the names from column A being given to cells in column B at corresponding rows. For example, cell B4 is named Radius. Edit names. New names can be created and existing names can be edited using the Name Manager, which can be brought up by clicking on the Name Manager icon in the Formulas ribbon. The Name Manager pane contains a list of all names in the Excel workbook and their references and descriptions. It also allows to create, edit and delete names using 3 buttons at the top of the pane. Clicking on the Edit button brings up the Edit Name pane that allows introducing changes in the name and in the reference to the named cell. Graphs. Next, we are going to discuss how to create graphs in Excel. Graphs. A wide range of graph types can be created with Excel. This includes column, line, pie, bar, area, scatter, radar, and so on. Excel has predefined styles that are sometimes not appropriate because they're too clunky and gimmicky. You can create your own style that can be saved for future use. XY graphs, scatter. This is the most common type of graph used in technical documents. It defines a relationship between 2 sets of values. The first step in creating a graph is to select columns containing the data to be plotted. The headings of these columns should be omitted. The graph is introduced by going to the Insert ribbon, clicking on the icon Scatter and selecting Chart Type. As you can see, the introduced graph has a default style. This style is not appropriate and can be changed. Let's see how this can be done. First, we delete the legend box. It is not required for a single series. To do this, we select the legend box on the graph and then delete it by pressing delete, or using the menu that pops up after clicking on the right mouse button. As you can see, the data in the second column is the limited range between 700 mm and 1100 mm. Therefore, we can reduce the range of data shown in the y-axis. This is done by selecting the y-axis and clicking on the right mouse button. In the menu that pops up, we can select Format Axis. This action brings up the Format Axis pane. In newer versions of Excel, this pane appears on the right of the spreadsheet and includes all the options discussed here. In the Format Axis pane, we can limit the values presented in the y-axis to the range between 700 and 1100. After clicking the OK button, the range of the y-axis changes to the defined one. The Format Axis pane also allows changing the format of how numbers are shown. This feature will be discussed later in this lecture. We will now discuss how to change other features in this graph, and this can be done using the Layout ribbon. Note that this ribbon is arranged in a slightly different way in newer versions of Excel. First, let's delete grid lines. One way of doing this is to select the grid lines icon on the Layout ribbon and then to select None in the drop-down menu and Primary Horizontal Grid Lines. An alternative way is to select the grid lines by clicking on them in the chart and then pressing the Delete button. The default line thickness in Excel is quite high. Therefore, we are going to change the thickness of the lines in the chart. This can be done by clicking on the line with the right mouse button. In the menu that appears, we can select the option Format Data Series. This brings up the Format Data Series pane. The line thickness can be changed by clicking on the Line Style tab and reducing the width of the line in the corresponding cell. As you can see, the line is much thinner now. Often it is necessary to add a title to the graph that describes the data shown. This can be done by selecting the Chart Title icon in the Layout ribbon and clicking on the option Above Chart to define the position of the title relative to the chart. In the window that appears above the graph, we need to type the name of the chart. In this case, LVDT Calibration. The next step is to introduce titles to the chart axes. This is done by clicking on the icon Axis Title, selecting the axis and title location. In the example shown here, the title is introduced under the horizontal axis. In the Axis Title window, we type the description of the data it represents, in this case, volts. The vertical axis title is similarly introduced. Note that the vertical axis title has several options defining its position and orientation. In the axis title window, we type its description. In this case, length. We can stay with this format for the graph, however, we can change it further if necessary. The formation of the chart can be saved for future use, and this is done by clicking on the Save Template icon in the Design ribbon. In the Save Template window, you should select the name of the template and where you save it. Graphing trick. New data can be added to an existing chart in several ways. It can, for example, be done by selecting the chart, which highlights the columns with data used in the chart plot. As you can see, the boxes around the columns have handles. Note that the magenta box represents the x-axis and the blue box represents the y-axis. Additional curves can be added to the chart by dragging the handle of the blue box over an additional column of data. This action results in the addition of a parabola to the chart. Extending the blue box over an additional column of data results in the addition of a hyperbola to the chart. The new curves are too thick. Therefore, their thickness can also be reduced. And the data shown in the chart can be manipulated by changing the size and locations of the magenta and blue boxes in the spreadsheet. For example, when the height of both boxes is reduced by one row from the top and bottom, the range of data shown in the chart is reduced. Functions. We will now discuss functions in Excel. As mentioned earlier, Excel has an enormous range of functions which are divided into several groups, including finances, date and time, maths and trig, statistics, lookup and references, databases, text logic, and information. In addition, you can introduce your own functions. Statistical functions. Here you can see several examples of statistical functions. The appropriate format of these functions is given on the right of this slide. When you type a function in a cell, Excel brings up a window explaining the sequence and meaning of parameters to be entered. Here you can see some trig functions. On this slide you can see two day and time functions and a logical function. Note that functions can be nested, which allows building complex expressions. Lookup and reference functions. VLOOKUP is an example of lookup and reference functions. Let's discuss this function in more detail. This function is used to extract data from an array of data based on its first column. This method is useful in many situations such as beam design, marking schemes, and so on. VLOOKUP works only when the data in the first column is arranged in ascending order. VLOOKUP looks for a given value in the first column of the array and extracts the value from its nth column. In the example shown here, VLOOKUP searches for the first value larger than 55 in the first column of the array. After finding the value 57 in cell A10, VLOOKUP goes to row 9 and extracts the value in the second column. This results in an alphanumeric mark C2, which corresponds to the numeric mark 55. Processing experimental data. Now we'll discuss how to process experimental data generated by your turbines in the lab experiments. Processing experimental data. Data recorded in the experiments must be converted to real values. To achieve this, transducers are calibrated before use. Voltage outputs from the logger should be converted back to real values such as pressure, length, or temperature. There are two common methods for doing this, including curve fitting and piecewise linear approximation. Curve fitting. Let's look at the first method. It starts with plotting the data on a graph, in which the x-axis represents the measured voltage, while the y-axis represents the desired output, that is, length, temperature, pressure, and so on. After plotting, the curve can be fitted with either linear, polynomial, exponential, or logarithmic functions. Here you can see an example of a linear and polynomial function. The goodness of the fit is evaluated in Excel using the coefficient of determination, or R squared. R squared ranges from 0 to 1, and the closer you are to 1, the better the fit. Let's consider an example of curve fitting. Normally, the process of sensor calibration yields data where the measured value, in our example length, is in the first column, while the voltage is in the second column. In the process of curve fitting, we need to rearrange the data. Voltage should be placed in the first column and length in the second. This can be done by copying column A into column C in the way shown here, after entering into cell C1 the condition that it is equal to cell A1. We can use the handle to copy this expression into the rest of the column C cells. Next, we select columns B and C. The chart is introduced by going to the Insert ribbon and selecting the icon Scatter. In the appearing drop-down menu, we select the desired type of chart. After these actions, a chart is introduced into the spreadsheet. As you can see, the chart is in a default format. We can delete the legend and format the chart as we discussed earlier using the menu brought up by clicking the right mouse button. Next, we modify the axes to get better use of chart space. The right mouse click on the vertical axis numbers brings up a menu. After selecting the option Format Axis in the Format Axis pane appears. In this pane, we limit the range of numbers of the y-axis to between 600 and 1200. Applying the same method to the horizontal axis, we change the range of the x values to between -5 and 5. And now the graph is ready to be used for curve fitting. A right mouse click on the curve brings up a menu where we can select the option Add Trend Line. This action brings up the Trend Line Format pane where the regression type and different options can be selected. The default regression type is linear. In the pane, it is necessary to tick the boxes Display Equation on the chart and Display R squared value on the chart, and this gives us the fitted function and the goodness of the fit. The trend line appears in black on the chart. As you can see, the linear fit is quite good as R squared is very close to 1. We can check if a better fit is possible. For example, we can try fitting the curve with a quadratic function. To do this, we can click on the right mouse button on the curve and select the Format Trend Line in the appearing menu. In the pane, we can select the polynomial regression type and set the value in the box order to 2. The resulting quadratic fit is much better as R squared is nearly 1. This expression can now be used for calculating the length from voltage. To get the expression, we should select it on the chart and press the keys Ctrl and C simultaneously to copy it to the clipboard. We select a cell and press the keys Ctrl and V simultaneously to paste the expression from the clipboard. To be able to calculate the length from voltages, we should do the following steps. As you can see, the quadratic function has 3 constants, O, N, and C. We copy the values of these constants from the fitted quadratic function to cells B18, D18, and F18, and name these cells accordingly. Next, we name cell B20 as the variable x. In cell D20, we type the expression of the quadratic function using the names of the cells. Now the lengths can be calculated from voltages by typing the x values. An alternative way for getting constants of the linear and polynomial fits is to use the function linest. As you can see in cell A11, this function analyzes two columns of data where the first column is length and the second is voltage. After clicking OK, cell A11 gives the first constant of the linear fit. You can see that it's similar to the first constant of the trend line expression on the graph. To get the second constant, additional actions are required. We need to select cells A11 and B11 and press the F2 key to edit both cells together. To enter the array formula, we need to press on the Ctrl, Shift and Enter keys simultaneously. Now the linest function is applied to both cells and will give both linear constants. Here you can see both constants calculated. As you can see, both constants are similar to the ones on the trend line expression on the graph. And note that the expression in the function box above the spreadsheet is in curly brackets, symbolizing the array formula. Now we are going to learn how to get the quadratic fit constants from the linest function. In cell A1, the linest function is typed in an extended form where curly brackets appeared after the second array. These brackets indicate to the linest function the order of polynomial approximation to be carried out. The default value in the brackets is 1. The sequence of 1 and 2 indicates that the linest function should carry out a quadratic approximation of the data, while the sequence of 1, 2 and 3 will result in a cubic approximation. Using the quadratic approximation, we get the first constant in cell A12. As you can see, it is similar to the first constant of the trend line expression on the graph. To get the other two constants, we select cells A12, B12 and C12 and press the F2 key to edit them together. Then we press the Ctrl, Shift and Enter keys simultaneously to enter the array formula. The linest function calculated all three constants in those cells. As you can see, the constants are similar to the ones on the trend line expression in the graph. Piecewise linear fit. The third method of calculating required values, lengths in our case, from voltages is to use the piecewise linear fit. This method is based on finding linear functions between consecutive sets of two data points. This can be done by using the functions VLOOKUP and INDEX. VLOOKUP is used to find data from the nth column of a table using the first column to detect the correct row, while INDEX is similar but uses a row and a column index to find the required data. To use this method, data must be sorted into ascending order. This can be achieved by selecting the data and clicking on the Sort icon from the Data ribbon. In the Sort pane, select the column to be used for the data sorting and check that box Order is set to smallest to largest to get to ascending order. This results in the data being sorted as required. Next, we use the linest function to calculate the contents M and C of the linear approximation of consecutive sets of 2 points. To use the index function, we add the index column with values specifying row numbers. Next, we select the values in columns B, C, D, E and F and name them as piecewise using the name box above the top left corner of the spreadsheet. We name cell I2 as volts and set its value of voltage to be used in calculating the length. To find a correct linear fit expression for calculating the length, we can use VLOOKUP. In the considered example, 1 volt is between minus 0.187 volts in cell B6 and 1.943 volts in cell B7, which is the range of the linear fit function in the index row 5. Next, the index function is used in extracting the linear constants m and c from the cells in column D and E corresponding to the index row 5. Cell I4 contains the linear expression required for calculating the length from voltage. Finally, the length corresponding to 1 volt is given in this cell. Any of the 3 methods discussed can be used for the analysis of data. Data processing. In data processing, the naming of cells can be a great advantage when dealing with large numbers of sets of data. It can be easier to use multiple worksheets rather than to keep all the data in one worksheet. In this case, each sensor can be analysed in a separate sheet and the results brought together on a summary sheet. It is helpful to check for any inconsistencies by plotting the data and the calculated values. It is important to ensure that graphs are laid out clearly, as it makes a visual assessment of data easier. And this concludes part 1 of the lecture about Microsoft Excel.